In Hill cipher, there's a couple of issues as well that you need to be clear of. And one of the issues is modding. So you need to be able to do the mod operation, which is normally a very simple one. For example, 10 mod, say 4, 10 divided by 2 is 2, and the remainder is 2. The remainder is 2, and that's really the mod. Mod gives the remainder of the division operation. Because we'll be doing encryption and decryption on an alphabet that has 26 characters, then we don't want any numbers or values that go bigger than 25. See, we will, as we've done in a couple of other encryption systems, that the alphabet will be given numerical values, A being 0, B being 1, C, D, and all that, all the way to the end. And in the English alphabet, then the numbers, or the characters will be given numbers from 0 to 25. That's from A to Z. So in order to encrypt any of these characters, if the value that the result comes out is bigger than 26, we need to mod it by 26. That's to reduce it, to make it come back to give us a proper value between A and Z. And in order to do that, we use the mod operation. So the mod function, it's a division function that will reduce any number and give us a result between 0 and 25. And it works normally, we have no problem. Most people have no problem with the mod operation. The only time is if the number is negative, that can cause some issues to some people. Maybe the easiest way, there are many different ways to do it. So if you find a way that you're more comfortable with, that's fine. But the easier way is to keep adding the number 26 to that negative number as many times until you have a positive number. So for example, minus 52, you add 26 to it, and add another 26, plus 26, plus 26, you get a 0. And that's it. Once you get a 0, any number between 0 and 25, you get, the moment you get non-negative number, that's then the end of the result of the mod operation. Oh, we'll try it out and we'll see how it goes later on. Right, so here's a quick example. If not, if the number is small, you can count backward as well through the alphabet. So through this grid, normally you go forward. And if you get a number that's 27, that means you count 24, 25, 26, 27 is the 0 and the 1. So modding a bigger number, positive number, you just keep cycling to the right. You keep counting, moving to the right. When you get to the end, you recycle back to here. But if you have a negative number, let's say minus 3, see the numbers go backward this way to 1, 0, and then minus 1 is here, which is, you can consider it minus 1 is same as 25, minus 2, minus 3, and that's where minus 3 is the equivalent of 23. And if you do the other, so that's one way of doing it, just moving, rotating backward to the left in a circular rotation. But you can also do the adding of positive 26 to minus 3. So if you have minus 3, you add plus 26, and the result is 23, which is pretty much the same. So those are the two techniques that are so simple and quick and easy, and we need. If you find a better way and you prefer it, that's fine, as long as you can come up with the correct value. Right. So there are here a few examples of few negative numbers. Right. Anybody can work out minus 66 mod 26? Minus 66, isn't it? So you add the number 26 to it as many times as it needs. So plus 26, that's subtracting 0, 4 in minus. And then plus another 26, oh, that gives us
minus 14.
That's 14. But that's still a minus number. You still have to add another 26 to it,
That's true.
which, yeah. So minus 66 mod 26 equals plus 12. So be careful, guys. Anyway, so there are a few examples here you can follow. Now, the inverse, once you work out the determinant, in order to calculate, to find out the inverse matrix, we usually start with the matrix that's used for encryption. Remember, one matrix is used as a key matrix for encryption, and to decrypt it, you need the inverse of that matrix. In order to create the inverse of the matrix, you need the determinant for that inverse matrix. And to get the determinant, you need to get the determinant of the original matrix and then get that inverse. And the determinant of the matrix will have to be a number in the modulo 26, the modular 26. It has to be a number between 1 and 25, and it has to be an odd number, and anything other than the number 13. So a number that does not divide by 26, with 13 it does, and a number that's relative prime. And to get the inverse of that, again, the condition is that if we multiply that, what number you multiply it into this number, once we get the original determinant and we need to get the inverse of that determinant, the two determinants, if you multiply them and multiply them by 26, they must have a remainder of 1. And therefore, in order to try, maybe say the inverse of 9, you need to multiply 1. So 9 times 1 is 9, which if you multiply 26, it's 1. 9, it's not 1. 9 times 2, or 9 times 3, or 9 times 2 is 18. 9 times 3 is 27. 27 multiplied by 26. That's a remainder of 1. 6 isn't, 45 is not that. So whichever one that mods it by 26 and the remainder of 1. And in this case, 3 is the number. 3 times 9. So the inverse of 9, the modulo inverse of 9, the modulo of 26. Inverse of 9, 9 times 3 is 27. 27 multiplied by 26, it meets this condition, which is the remainder is 1. And therefore, 3 is the inverse of 9, the modular inverse, when the modular is 26. And we'll be using modulo 26. So let's start. These are the two things we need to know: how to actually mod a negative number and how to find out the inverse of the determinant. So these are the general steps to create the inverse of a matrix. Make sure all values are within the modulo that we are working on, which is modulo 26. So we'll modify the matrix and the numbers in the matrix to make them between 0 and 25. No negative numbers, no numbers higher than 25. And then calculate the determinant for that matrix. Then find the determinant for the inverse matrix and create the inverse matrix. And be certain, make sure, it's a good idea to multiply the inverse that you created with the original matrix. And if you multiply any matrix into its inverse, you should get the unit or the identity matrix, which is a zero matrix with ones in the diagonal part. So let's do it. Now, one thing to notice, if you take a matrix and find its determinant, and if its determinant is not one of those numbers, it's not an odd number, then that matrix has no inverse. There's no need to carry on with it. And you cannot use it, maybe, to encrypt because there's no inverse matrix to decrypt the message. Right. So, I don't know if they have an example here. Here's an example, 26 modular inverse matrix. Find the 26 modular inverse of this key matrix. Let's say we want to use this matrix for encryption, and we want to find out what's its inverse. Or maybe this matrix was used. In fact, you can even use those negative numbers to encrypt when you are encrypting. They give you the same result whether you use the inverse. If you want to encrypt a message, you can encrypt it using any matrix. No matter, it's not modulo in there. But after encrypting at the end, the result, you'll have to modulate it. You have to bring it to modulo 26. So sometimes it's better, even with your key matrix, this matrix you're going to use, change it into a modulo matrix right from the start. But it will work, even if you use it as it is. But then when you create the inverse matrix has to be a modulo 26. Now, there's too much talk about it, but it's quicker to do it. So let's work out. Let's change, first thing we want to change this matrix into modulo 26 matrix. And so every number needs to be modulated. And so any number divided by 26 and get the remainder. So 5 divided by 26 is 0, the remainder is 5. Same with 8, so any number less than 26 will not change. But minus 9 modded by 26. Okay, so you add plus 26 to it, plus 9 becomes 17. So this matrix is pretty much the same as this matrix modded 26. Like, we have not really changed the matrix as such, but this is the same matrix in a modular format. Now, find the determinant and its multiplicative inverse. So let's find the determinant of this matrix. This is the original matrix now we're talking about, but it's modeled. So the determinant for 2 by, yeah?
For the survey, like if we get first determinants and then if we change the determinant with mod 26, is that the same thing, isn't it?
Yeah. So this reduces the problems and issues. So the mod for this one, or the determinant for a 2 by 2 matrix, multiply those two, 5 times 3, minus 17 times 8, and that's minus 1, 2, 1. Now we need to bring the modulo of that, minus 121, and that's the result. So if you have a calculator that does the mod calculations, it will probably help. Now, the determinant for this, the modulo 26, the determinant is 9. So now we want to create the inverse matrix, and we need to get the inverse of the determinant. First, does this matrix have an inverse? Does this matrix have an inverse, or it does not? It can never have an inverse. It does, because its determinant is an odd number between 1 and 25, and it's not 13. So now, what's the inverse of the determinant of this determinant? What's the inverse of 9 within modulo 26? So you multiply the numbers from 1 to 25 into this number, multiply by 26. If the remainder is 1, then that's our inverse. Yeah, but if you have that table, if you have this table, if you can remember it, or one way of working it, there, the 3, its inverse is 9, or 9 is 3, so it's. But why not 11? Because 9 times 11 is 99. If you mod 99 by 26, the result is not 1. There's only one inverse. And these are the inverses. So the 3 and the 9 are the inverse of one another. The 11 and 19 are the inverse of one another. So it's really in each half of this table too, if you want to remember. But you can work it out, you can calculate it. Right, so we got that. So that's the first and second and almost third step. So we found the determinant for the matrix, and now we have the inverse determinant. Now we're going to create the new determinant inverse matrix. And to get the new inverse matrix, you need the adjunct matrix. So here's our original matrix. For modulo 26, 5, 8, 17, 3. Now we want to get the adjunct that will help us create the inverse of this matrix. And the adjunct, you swap those two numbers in this diagonal line, and this diagonal line change their sign. So this is the adjunct matrix. All I have to do now, multiply that new determinant, its determinant into it, and that will give us, so the new determinant that we worked out, the inverse determinant, is 3 multiplied into the adjunct matrix. 3 times 3 is 9, 3 times 1 minus 8 is minus 24, and so on. Now, this has numbers that are bigger than 26 or smaller than 0. We need to modulate it to 26. So we change it into modulo 26. And 15 don't change, but plus minus 24, if you add plus 26 to it, then the remainder is 2. That's really minus 24 mod 26 equals 2. And minus 51, you add 26 to it, equals minus 25, and then add another 26 plus 1. And this is our inverse matrix. So that's as simple as it is. So in order to get the inverse matrix on a modulo 26, if you have the key matrix, first work out the determinant for that key matrix. First convert that matrix into modulo 26, gets its determinant. If its determinant is an odd number between 1 and 25, and not 3, then it will have an inverse. To get its inverse, you have to get the inverse determinant, which we got at 3, and we have to get the adjunct matrix and multiply it to get the inverse matrix. Yeah?
Considering we're always performing the mode 26 operation on the matrix, is it possible to also have a determinant more than 25? Okay.
You correct it to plus 26, modulate it.
Okay. The previous
We had a determinant that's minus 118 or something, I don't know what. This is our original, our matrix, and had a determinant minus 129, 121. It can be plus 121, then you have to mod it. When you mod it, it's going to be between 0 and 25. Once you mod it to 26, it has to be between 0 and 26, yeah?
Yeah, so I was looking at the condition for the matrix to have an inverse. You said first is...
Yeah, you mod it first, and then once you mod it, once you mod it to 26, then it has to be the number between 0 and 25. If it's 13, then there's no inverse. If it's 12, there's no inverse. If it's an even number. If it's an odd number, other than 13, then it's okay.
The 0 is there an inverse?
0 will not be acceptable either. If you scale it, then all numbers will be 0. No, it won't. A 0 will not work. Okay, so it's simple. Right now, let's make sure, and always do that. If you have a key matrix and you got the inverse matrix, are they really the inverse of one another? So these are the two matrices now that we're saying this one is the inverse for this one. Are they the inverse? How do we know they are the inverse? Let's multiply them. Multiply both of them, this one into this one, and find out if they are the inverse. And here's the actual result. So multiplying, you multiply this line into this column and add the product. So 5 times 9 is 45, and 8 times 1 is 8. So it gives us that's known as the identity matrix. So yes, this matrix is the inverse of that matrix. Okay, I'll fly through the example. I don't want to go through. Okay, let's go through this example quickly. Now, find the 26 modular inverse of this matrix. First thing, it's already, all the numbers are smaller than 26. There are no negative numbers, so that's fine. Let's find the determinant for this. The determinant for this is 2 times 2 minus 25. I think, yeah. So it's 4 minus 25, it's minus 21, and that's modded, it's 5. So the determinant for this, the modulo 26 determinant for this one is 5. 5 is an odd number between 1 and 25, and it's not 13. Then this one has an inverse. To work out the inverse matrix, first get the inverse of this determinant. And you can check the table, or you can multiply 5 times 1, 5 times 2, 5 times 3, until you get a number that, if you multiply it into 5 and multiply 26, that gives a remainder of 1. And it seems to be, I don't know. Anybody knows what the determinant, the 21? 21? Oh, okay. Yeah, according to the table here, 21 and 5 are the modulo of 26 inverse of one another. They're both prime numbers or relative primes to one another. See, 15 is not a prime number, 21, but with 15 are relative primes. They don't have something in common, and therefore according to the modulo 26, the remainder of their product is 1. There's no number that will multiply and give up, to both of those. Okay. So now we got the new determinant, 21. All we need is the adjuvant of the original matrix. This is the original matrix, 2, 5, 5, 2. Adjuvant is swap these two. Okay. So the 2 is swapped with this, and we change the sign of those, and the new, okay, that's the determinant, and then we put the new determinant, which is 21, did we say? Multiply it into the adjuvant. So that's the new, that's the inverse matrix. This is the original one, and that's the inverse. And if you multiply them together, you should get the identity matrix. And this is the proof. Now, to encrypt or decrypt let's say decrypt. Let's say we got a message. This message was encrypted using one of the matrices, the original matrix. And see, these are the two matrices. This is the key matrix and this is its inverse. This was used to encrypt a message. And encryption is exactly the same. You take the message, multiply it into the matrix, and that will encrypt it. Take the other matrix, multiply it into the ciphered message, it will decrypt it. So now, let's go through the decryption. It's exactly the same. So we're going to use the inverse matrix to bring back the message. So the message, this is the kind of question you might get. Use the inverse matrix. This, you probably won't get the question. This is an easy question. You get a question like this. This matrix, you're given this matrix and you're told this matrix was used to encrypt a message, and here's the ciphered message, part of the ciphered message. Decrypt it. Now, in order to decrypt it, you have to go through this process of creating this inverse matrix. So you have to know how to decipher or to change the key matrix and extract the inverse of that matrix and prove that it is the inverse. Now, we're going to use now that matrix to decipher this message. I'm always using this grid for now, A to Z, 0 to 25. So to decipher it, we take our matrix, this is the inverse matrix, we use it for deciphering. And we're going to decipher the character I, J. This is 2 by 2 matrix, then it can decipher 2 characters each time. If it's 3 by 3 matrix, then it can decipher 3 characters in the message. If we use 5 by 5 matrix, then we can take 5 characters each time of the message. But this is like a block cipher. How big is the block here? 2 characters, depending on the size of the matrix. So this is a small matrix, can only take 2 of these characters at a time. Of course, you'll have to convert those characters into numbers based on the grid that we have. So I and J are 8 and 9, and whatever T and P, that's 19 and 15. So that's what we want to decipher. Usually we don't write IJ here, we just put the 8 and 9, but I'm just telling you I is 8 and J is 9, that's why I have the 8. And this one should be. This is correct. This is not, definitely not 9 and 5. 19 and 15. Oh, yeah. Okay, so it's 16 times 18. Plus 25 times 9, 16 times 8 times 25 times 9, you add them together and you get 358. But 358 by 26, you get 15. Convert 15 in the grid, and it's P. This character J, which is 9, so we just have 9 here, multiply. No, we haven't finished the second line. So the second row, 25 times 18 and 16 times 9, so 344, what 26 is 6 is G. So the I is converted into P, the J is converted into G, and so on. Same with this one, except this one is 19 and that's 15. T is 19 and P is 15. And if you multiply those two matrices, you get 3 and 13, which is D and N. And this is just PGDM, postgraduate diploma in networks. Maybe it doesn't make sense to most of you, but okay, so that's just usually the clear message should make some sense to us. This one is a bad example, but but that's the actual ciphered message, and that's the deciphered message. And PGDN is just, it means postgraduate diploma. So if you start the course here, a master course, and if you don't finish it, you can exit with a postgraduate diploma. Which I hope none of you will. I hope everybody will get the master. Okay, I'm going to stop this. This is an idea of what, and this is almost also an exam question, using Hill cipher to decipher a message. It involves creating or generating the inverse matrix that's used for deciphering. So we'll have an example next week on this. Any questions now?
Will the inverse table be given?
Say again?
The inverse table will you be given during the exam? So the inverse table.
Yeah.
You also say,
The inverse for the determinant.
yeah, will the table be given?
No. You'll need to do this multiplication and find out. After a few examples, you'll realize, you will remember, the 3 and the 9 and the most common ones are so easy. So there are only, how many numbers are there? First, the 1 and 25 doesn't change, so they're the same. 2, 4, 6, 8, 10. There are only really 5 of them because they're all reversed. They have the same. 3 and 9 is same as 9 and 3. 5 and 21 is same as 21 and 5. No, you don't get this with them. So you'll either work it out yourself or remember the numbers.